So let's start. Hi everybody, good morning. My name is Nico Josuttis. I come from Germany, and it's all my fault if you complain about C++, because I am involved since 1995 or 6 in the standardization of C++. I've written some books about this, and I still write some books about it. And as you probably know, as you are probably C++ programmers, we have two different standards. We have standardized the old C++ standard in 1908, which got a bug fix in 2003. And then we started with modern C++, which started in about 2011. And now we have a 3-year cycle, so every 3 years we have a new standard. So what has changed? What does it mean for the ordinary programmer? What does it mean for people who just want to write the trivial class? And believe me, this is a talk where if you come from another language, you will tweet immediately that C++ is a problem. Yes, it is, but it's a fast problem. And that's a good thing. So, general disclaimer. 2 things I have to say. If you use strings, there's something called the short string optimization, which means normally strings need some memory, but strings today, usually if you only need 15 characters, don't need memory because they reserve something inside for up to 15 characters. So as my examples have to fit on a slide, there are strings that have 3 characters, so just assume they have 16 characters instead, so that you get the general view, because we talk about allocations in general. And the other thing is, I use the modern way of initialization, which has changed over time, which means I used to initialize, I use curly braces and no equal sign. Timo will, in the next talk, say something about that. Just a short summary why this is better. So we have the 3 options to initialize an int. The former way we got from C with an equal sign, then from old C++ with parentheses, and then with curly braces. Curly braces is better because it's easier to make sure that an int is initialized. Just use empty curly braces. Empty parentheses wouldn't work because then this would be a function declaration. And that works with any type. You detect if you lose some data, for example, convert a signed int to an unsigned long, then this is an error and is detected as an error, which is good. It works with auto, finally. We made a mistake there in the past. It is self-explanatory. This creates a vector with 2 elements. One is 8 and one is 15. If you use parentheses here, this is totally different, totally confusing, because it creates 8 ints, all have the value 15. If you think this is better, you are screwed up by the errors we made in the past C++ standards. So this is a problem. Yes, change is a problem for people. So beware, yes, things can be easier and more self-explanatory, and that's better, not worse. And we have other examples. For example, this declares a hash object and then uses it as a function. If you use just parentheses, this gets more confusing. Let's initialize a vector of int with some members read from an input stream. This will not compile at all. Well, this will compile at all if you use parentheses instead, but later on you get crazy error messages because then you declare a function here instead of creating an object. And it's the only way to initialize an enum, and you can use it to initialize an aggregate even with base classes since C++ 17. So a lot of good reasons to use curly braces, and for the detail, Timo will tell you all. Not most of it. Okay, so having said that, let's start with the trivial class. The trivial class is a customer, and the customer has a first name, a last name, and a value. So we have 2 strings here, first and last, and we have a value, which is, for simplicity, an int. And how did we learn to program that? Well, this is a constructor just to create objects. Let's take 2 strings and use them to initialize the first and the last name. These 2 strings are passed as we learned it by const reference. So that means let's avoid to copy the parameters when we pass it to a customer. I would assume that everybody of you learned it that way. I'm not sure you'd still do it that way, but let's talk about it. So let's create a customer initialized with Joe, Fix, and 42, and now you want to complain and say, hey, this guy wants to use curly braces. Yes, of course, we switch to curly braces now. That's the modern way we use. But it doesn't matter for the details here. It's just syntactic sugar. So how many expensive string calls do we have here? In other words, how many potential allocations? In other words, if we would not have the short string optimization, or if these strings would have more than 15 characters. 4. You're experts here. So why 4? Because in the data segment of the program, we have these two string literals, Joe and Fix, and they are used to call the constructor. The constructor creates F and L, which is a different type, so you have to convert these string literals to a string. That's the first two allocations. And then we can use these two strings to initialize the members first and last, which means we have to copy them into first and last. So that's the next two copies, the next allocations, because a copy is a full copy of the thing before, even with Move Semantics, if you heard about that, because this is an object with a name, and there's no optimization saying that this can lose its value. It's just there has to be F and the initialized value are first after the initialization in the constructor. So we have the object created, and in fact, we delete the temporary objects, F and L. So, and we did this with 4 mallocs. 2 to create a string, 2 to copy a string. That doesn't look perfect. So let's do better. First thing to make it better, well, why convert to string, just overload for character star? Because we pass a string literal. And yes, indeed, this is just 2 mallocs because we initialize the members first and last just by the past pointers to an array of characters. Of course, we want to combine these things. So if we then pass a string and a string literal, this should also be perfect, but with this, this will only call the first constructor. So because it converts, because we can only use the first constructor, so we have the conversion problem against for the second parameter. So in other words, to make it perfect, let's overload for all different cases where one of the arguments might be a string and the other might be a string literal. It's easy to do. It's a little bit of boilerplate, let's say it that way. But OK, we are fine. Good. If you use Move Semantics, by the way, things are not better here. If you have heard about Move Semantics, you say, hey, I no longer need the value of S here, but it doesn't matter. It will still perform the same way. So that's 2 mallocs, 1 copy, and 1 create. Because again, this will call this constructor, and we have to pass. We pass this moved S to a string, but this is a const string reference, so it will not forward the moved value to the string here. So we have a new option here, since C++11, to make this better, or also to optimize the creation of temporary strings here. Let's implement these constructors with Move Semantics. And that looks that way. We would overload for the ordinary way when the past value is still necessary. And we would say, if I can steal the value from the thing I get, which applies to temporary objects and to moved objects, let's take the value and move it into my first and last name. And that means that we would say, for example, if we initialize a customer with Joe and Fix, we would still create F and L as temporary strings, allocating memory if we don't have the short string optimization. But then we can steal this memory to initialize the first name and to initialize the last name. And that's our new object. And we have only 2 allocations here. And that will work. Good, fine. Problem solved. Oh, yes, and we need all the combinations, of course. So we have to do all the 4 overloads. Good. Fine. Perfect. Oh, no. Damn. This is ambiguous. Why that? Because this passes an std string, a temporary string literal, which can convert to a temporary string. We have two functions taking a temporary string as a best match. Both have default values, so the compiler does not know what to take. The problem is that we have too much default values here, so let's remove one of them, and this compiles fine. We are not at the end of the story, it goes further. But you got the idea of the talk already, I think. So, let's initialize this with an equal sign. Yes, I told you I want to initialize with the curly braces, but people still like this, and even I like this. I don't follow my style guides myself all the time, so don't do it either. So we have here the problem that this is two implicit user-defined conversions, and that's not allowed if you use the equal sign. That's an explicit conversion. So this will not work. We still need, this is in general does not work, two implicit conversions if you initialize with an equal sign. So let's overload for everything. So that's 9 overloads, and the good thing is we have only 2 string arguments. If we have 3 string arguments, we need 27 overloads. This is good. Well, this is at least perfect regarding the performance. We have only 2 mallocs here, 2 mallocs here, 1 malloc here. This is exactly what we wanted, and everything works. So what can we do instead? First of all, why don't we just pass by value? Well, if we pass by value, we always create a new object here, and then we create a copy to initialize the first and the last name. So we have 4 memory allocations, 4 here, 3 here. That's 11 altogether. That's far too much. But we have move semantics. So we can say, let's create the arguments f and l as a string. Let's create them. And then let's move them into the first and last name member. And that's surprisingly good. It fits all the cases we have here, and it is perfect regarding the number of allocations, because the trick is simple. We say, in any case, we have to initialize the first and the last name as a string. The only thing we do is we do it earlier, here in the argument, and then we move this memory that is initialized here to the members. So this is, from the number of allocations, perfect. We have more moves than necessary. So, but yeah, that's 5 allocations in total for these whole examples, when we had examples where we had even 11 here. Okay, yeah, and we need this thing. Good. So to handle 2 allocations. So this looks like we are done. Fine. Let's keep it that way and think about another alternative. Because another alternative we have in C++ is perfect forwarding. We have a concept saying there's a mechanism that you can say a function can take an argument and pass this argument perfectly forwarded to somewhere else. And this is, in fact, something we need here. Who has heard about perfect forwarding? Who has used forward, std forward? Okay, but not all. So here's how it looks like. There are a couple of rules you have to follow. The rules are, you have to specify the arguments to be template parameters, then declare them with $, and then use forward instead of move to forward them into the customer. Because move could be wrong here if you pass something where you should not steal the value. And this move, this forward, is a move if it's allowed to steal the value from the thing you pass. That's roughly it. So this covers, in fact, all cases we have. It covers them all. So Because the trick is here to say, well, let's initialize an object with 3 arguments, and the first 2 arguments, whatever the type is, are used as F and L. Whatever the type is, we don't make any conversion at all. We don't create anything. We just say F and L is a different name for something we passed. And then we say that what we have here is used to initialize first and last name. And because now we have here as 2 string littles, and we need an std string as a member, we create them there, and we have our C, and that's it. Perfect. 2 mallocs. No, even not a move here. Does it work here? Yes, 2 mallocs. Does it work here? Yes, 1 malloc. Done. Okay, thank you very much for your attention. Oh, wait. Tell me your question.
So what about the right side of the argument? So before we had the consequences which guaranteed the parameter to be kept alive. Is that going to keep it alive as well if we pass a temporary string?
If you pass a temporary string here, so this you can say it's similar to the move case. If you here create, say, something, you have something that returns an std string, then this temporary string is passed here by reference. So F is just another name for your temporary object. And as you enter the stack, you don't leave the stack. This object is still there while the constructor is running. In the implementation of the constructor, this is copied into, this is moved into the first name. So it works, yes. So are we done? Let's add 2 or 3 other simple cases. This is the first one. When I made this talk, I thought, I'm done now. But, well, let's start with another simple test case. Let's create and initialize a customer F initialized by a string literal Nico. So use all the defaults here. So this was the first thing that didn't compile. Why that? Because there's a rule when you use templates in C++ that you can't deduce the type of template arguments from default arguments. It's simply not allowed, supported. So the compiler will tell you, I don't know what S2 is, what the type of the second argument is. Although there's a default, the type of this default is not used. So the first thing you have to do is, please add a corresponding default for the second type name here. Good, done. Let's try out something else. Let's try to copy a customer. Okay, customer G is initialized by customer C. This is calling a copy constructor. And my compiler says this does not compile. It does it with a very strange error message, something like, I can't initialize this string by a customer. What? Okay, even more suspicious, let's create a const customer, and let's initialize a customer from a const customer, and that compiles. So what's wrong here? The problem is easy. This template is used as a copy constructor in some cases. It is used if it's a better match than the inbuilt copy constructor. So the inbuilt copy constructor initializes a customer from a const customer. So if we pass a const customer, this is a perfect match. The copy constructor will be used. But if we pass a non-const customer, we have a type conversion. We have to convert the past customer to a const customer. That's a very simple type conversion, but it is a type conversion. And according to the rules of C++, a template argument that does not need a type conversion is a better match. So that means this is preferred with the first argument is just a cast. So we initialize, we say cast is taking a cast and these defaults, and then the compiler tries to initialize the first name by this customer. And that's the error message. We love C++, huh? Okay, so how to solve this? That's pretty easy. You just have to write this code. Say it? No, because the move constructor is anyway implicitly declared. This does not solve the problem. Sorry about that. So, we just have to say here something that says, disable this constructor if we can't initialize the first member from the past first argument f. And that's the way you program that in C++. So that's one way to program that. And you add an additional template argument, which you don't need. It's just to have somewhere the expression enable if, which is a nice trick of templates, a scary nice trick, well, a bad trick, a helpful trick, let's do it that way, to say if this condition is true, we enable this whole thing. Otherwise, when we compile, we assume this constructor doesn't exist at all. So we say, enable this if S1 is convertible to std string, and the rest is syntactic sugar. As you probably know, if you know C++, what to write here, and the number of angel brackets have to fit, etc. So it takes a little bit until it works. Good. Is this the way we want to program? Well, I have my problems, but we do this trick in a couple of places in the standard library because the standard library is written by experts. They know what they do. They do. Who was laughing about that sentence? Usually we know what to do. We are humans. We make mistakes. Okay. So it's getting a little bit better. So with C++ 17, this looks a little bit better. And with C++ 20, as far as I know, this will even look a lot better because we can specify then requirements and say this constructor requires that the first type is convertible to std string. Otherwise, it's not visible. It's not there. That's not guaranteed that we will have it in 2 years or 1 year. Good. So we are done. We have found a couple of ways to initialize a customer with 2 strings. So just the traditional way, const string references, and then initialize the members, 10 mallocs. Then the new way with Move Semantics, just one overload, an std string, and move it inside. Then overloading all the different versions. And then this interesting new way to say, let's use perfect forwarding, but then we have to deal with the fact that this might be used as a copy constructor. Good. So which one is right? The answer is all 4. It depends who you are. It depends about the knowledge of the people who program. It depends on the amount of usage of your library. If you just teach C++, forget about all these 3 things. We don't teach move in the first week of a C++ programmer. I hope we don't do. That's our goal. There are other more complicated and more important things. So, so this is probably for beginners. So this is for beginners. This is a way if you are an advanced programmer. This is a way if you are foundation libraries, because you save some moves, and moves also cost time. And this is if you want to keep your job forever. As we do in the library. So, okay. At this place, now usually a couple of questions arise. Yeah, we have some time. So for the first question is, but we have something cool and new in C++ 17, which is called string view. Who has heard about string view? Okay, so isn't this the solution of everything? To some extent, you have the impression that this is what it is. Well, so the question is, if we initialize the customer with an std string, is it just a solution if we take an std string view, which is just not creating its own memory? It's more something like a string pointer, looking like an ordinary object, but very dangerous in usage. And so yes, indeed, it saves one UR malloc if you pass a string literal. No curly braces here, oh my goodness. But it acts a new malloc for this case. So if you have a temporary string returned, the problem is this takes a string view, so the temporary string becomes a string view, which is a cheap conversion, but then the string view is then used to initialize a string, which then allocates memory. So which is an expensive call. So this is not better. With std string view, you still need a couple of overloads. The lesson learned here, don't use string view in a call sequences that finally need std string. Start to use string from the beginning. So the other question that arises, does this only apply to constructors? How about setters? So should we, if we have in our class now a setter for the first name, should we use passing const reference, or for the same reason, because we anyway have to create or initialize or set a first member, pass by value and move it in? Well, let's look into details. This is an application of this. So let's create two strings, a short string and a longer string, and let's initialize the customer C and then set the first name to N, then to Konstantin Alexander, then to N, and then to Konstantin Alexander again. Thanks to capacity management of C++ string types, this will only allocate once. I mean here in this. The setters. This will not allocate at all because we already have space in the string member for 3 characters, so we don't change this. But the moment we have to grow, then we have to malloc, and that's good enough for all the other setters. So that's a pretty cheap operation already. So the alternative would be that. And that's, look what happens. Because if you take this by value, you always create a copy first here, because this is not a temporary object, this is an object that afterwards still exists. So in all cases, we create a copy, and then we move it in. This move assignment to first is internally usually just a swap. And by swapping this means that we, even if we assign n, we shrink the capacity of the first name so that it's not good enough to use more memory. So while the traditional way will always only enlarge the member first, and it's very probable that after some running of your program, I don't know how often people change their first name, but there might be other examples. So after a while, this is stable and will not allocate at all, which is a good example that the defaults don't work that bad. But here we will reinitialize the capacity because we always create a string which has enough capacity for whatever we pass here. So this is not an option. This might shrink the capacity, and this is not something you should do. Please use for setters the traditional way. And thanks to Howard Hinnan and Herb Sutter was pointed it out years ago. So let's talk about getters. Then we have everything. Let's create an object that sets the member. Let's get the member. So how about that? Okay, here it is. Let's start with get last. This should be get last name, but I need some space on the slide. So this is just get last. And this get last, as you can see, we start with the version returning this by value, which is pretty slow. It works fine, but it's pretty slow. So if we have a customer C and we call get last, we will create a copy of the last name. And that will then be used, and if it's temporary, it will then delete it immediately. If you, for example, have a vector of customers, you iterate over all the color customers, then you call get last and check something. This might be, I measured it yesterday, something like for 1 million customers in a vector, take 150 milliseconds instead of 30, or even 3. That's 5 to 50 times slower. That's probably the reason that a lot of programmers say whenever we get something, we have a getter, we access a member, let's return it by reference. Who would return by reference here? Const reference, yes, of course. Who would return by value? Who has no clue what this talk is about? That's good, okay. So let's compare to return it by const reference, and we are significantly faster in all these cases. And that's good, great. So are we safe? Wait. So first of all, some people think about if this object is modifiable, we can even return by reference non-const, which means we get access directly to the member last with this. So we can say something like c.getLast equals Timmy. And you know that in a couple of classes, that getLast is named operator brackets. So the index operator is implemented that way. Wait a minute. Think about we have some reason to protect the access to the last name. We want to make sure that our last name is not empty, which we can do if we can intercept in all the API calls that set the last name. So in the constructor, we can make sure the last name is not empty, and when we have a setter, we can make sure the last name is not empty. So if we now have getLast returning a non-const reference, we have broken this encapsulation, and somebody can say getLast equals an empty string. So this breaks encapsulation, and this is just one reason this is not good, usually. So how about just const string reference as a getter? Everything is fast. This is an error. This should not work. It should not break, give direct access to our members. Good. Perfect done. Once again. You have seen that before, perfect done. Whenever there's perfect done, you think you're done, but there is something wrong with this. So what's wrong with this? Well, let's loop over the characters of a name returned by a temporary, by a function that returns a customer. So let's have a function read customer. Let's read the customer. It returns a new customer, a temporary object. And now let's use this new range-based for loop to iterate over the characters of the last name. What happens here? Core dump at best. Why that? Why the hell is this a problem? Well, this is the implementation of the range-based for loop as it is specified in the standard. And it works the following way. If you have the range-based for loop, it's, you take the left part of the column as an initialization inside the loop, and the right part you take as an initialization before the loop really happens. So we initialize something that is used to where we iterate over all the elements. The problem is, what we initialize is something, a handle, because we need read, cast, get, last twice. We need it here to call begin, and we need it to call end. We call, for this last name, begin and end. So what we use here is something that is similar to a template parameter used to forward the arguments, which is a universal reference, which unfortunately in the standard was named forwarding reference because they don't like that the community already has a name and they wanted to confuse the programmers. And this forwarding reference has a rule. Usually a reference extends the lifetime of what was used to initialize it. So usually this is safe. Even if you return a temporary object, this extends the lifetime. But only if the thing you have here on the right is used to initialize this. It does not extend the lifetime of indirectly returned things. So this will extend the lifetime of what get last returns, but it will not extend the lifetime of what read cast returns. And that means read cast returns a customer. We call get last. Get last gives us access to the last name of the returned customer. And then the temporary customer gets destroyed before the loop actually starts. And that means that we have a fatal runtime error here. It might work if we accidentally find still our characters there, but you might get a core dump, and as you know by Murphy's Law, you will get the core dumps when you release your software in production. So don't do that. This is a general problem we have in C++. Whenever you have a function returning a reference, if you use it, if you call it for a temporary object, there are problems. Don't do that. And so one caveat here might be, if you have a function returning an by reference, don't use this as expression in a range-based for loop. The same would be true if we would return something and we use the index operator here. Just if we return a string and use the index operator. The same problem applies. So if you want to be safe, maybe it's better not to implement the getter to return by reference. Maybe it's better to return by reference. Yeah, maybe it's better to return by value, because then all the critical, fatal runtime problems are gone. This loop works because we create a copy of the last name, and then the customer can die. We still have the copy of the last name of this temporary customer. But now we get slow. How can we deal with that? Well, first of all, the rule is don't let getters return by reference. End of discussion. I don't discuss it with you anymore. Then with I/O, there's an exception because we have this strange rule that we always have to pass the O stream by a reference, or the input and output streams. But now you might say, but Nico, performance is key in our application. So is there a way around? Yes, there is. Here's a trick. This is an overload of two getters, and it's not the usual overload you might know, which is one is const and the other is non-const. This is a different overload. This different overload says, we have an overload here for 2 ampersand. This is as if we would have declared this passing a parameter by 2 ampersand. And what does it mean, 2 ampersand? Move semantic. We have a temporary object where we can steal the value from. So this would be called for temporary objects, or where we can steal the value from. And this would be called in all other cases. So we have here a slightly different rule, say, don't return references to members of temporaries. The technical term we use is PR values. So if you do that, look at this. This gets fast because this uses this. This gets fast because it uses this, because we have a name here. And if we have something that has a name and we call get last, then we pass it by reference because it still outlives this call. So this will be called, and we will not unnecessarily create a copy of the last name. Here we have a slow, and this also applies here. So if we have a temporary object and we call get last, can we make this faster? Yes, we can. Because this is a temporary that's about to die. So let's steal the last name from it. So when we create a temporary customer, let's return the customer. This customer, when we call then get last, and this temporary customer is about to die, we steal the first or the last name from this dying customer. And then it dies, but it's no longer the owner of the string, and we return the string by value. But what we return is just the memory that was originally allocated for the last name in this customer. And that's perfect. It's safe, and it's fast. Yep. Say it again. You mean that you say here an ACID string with 2 ampersand? Well, nothing prevents you from doing that, but it can be significantly false if you do that wrong. Because then you return by reference, and you shouldn't do that, because you return then a reference to a local object. Returning by reference should only be done if the thing you have inside outlives your life. So return values declared by 2 ampersand is a very, very, very rare case. And you'd only need it in template code, in generic code. Don't do that. So that's it. That's it. And that's the lesson start. That's Move Semantics for Trivial class. So our constructor looks a little bit different. Pass by value and move. Setter, look as we have learned. Getters, you can overload for temporaries and everything else. And if you have temporary, you can move out the value of the member by value, and in other cases, you return a reference to it. This is obviously nothing for beginners. This is, again, the different levels of C++ knowledge we have, and this would be, I would teach that, or I teach that in my advanced classes. Because the ordinary default is fine. In many cases, until performance is very important, but if performance is so important that you want to optimize things, you should really understand what you do. And maybe you have understood more now than you knew before. So, summary. Take it easy. Implement as simple as you learned. No std move, no 2 ampersands. This is still faster with this is still got faster with C++11 because under the hood, in many cases, Move Semantics is used. And getters should return by value. Don't trust people who tell you something different. Don't place expressions at the right side of a range-based for loop unless you know that there is no function involved that returns something by reference. This is just, the range-based for loop is only one application of this problem. I could create others. The range-based for loop is the most intuitive one and the most one where you don't see the problems immediately. So don't ask for reference access to temporaries. That's the general problem we have, because the lifetime of the temporaries is not extended. And finally, if performance is key and you know what you do, use Move Semantics and Constructors or overload all options. Overload the getters for the two cases I told you, and don't use Move Semantics and setters. We have a meta problem. We have a second summary here, which is C++ is complex, as we have learned now. We'll take it easy. Defaults are fine. Keep it simple and stupid. Optimize if it's worth it. Usually Mather first. You should only be perfect if you write foundation libraries, libraries that are used by thousands and millions of programs and programmers, which is some reason we, for example, have all the overloads and use forward in the standard library in a lot of places. And the problem is we need style guide. We need more style. We need modern style. There was a past 20 years ago when we had people like Scott Myers writing books like Effective C++. He has retired. Nobody is writing these books. Somebody has to write a short book about what I told you just here. And we need other lessons like that. How to deal with modern C++, because we invent so much with each and every version of C++, and we have a problem to understand what to teach, what is safe, and what you should avoid. That's our meta problem. We need different style guides, by the way, for different programmers. So that's it. Here are some books. This is just advertisement, just one hint. I'm currently writing a book about C++ 17, which you can download for a cheaper price this week. And this is written in an agile way, so you get all the updates for free. It's only 90% done. It's an ebook. That's it. Thank you very much, and I think we have 2 more minutes for questions. Yeah, thanks.